whoever's not here, so can listen to the. Okay, guys. Today we'll be finishing on chapter 2. I think the quiz is already there for you. I have to just reopen it, and so we'll finish chapter 2, and then we'll go from there. So we are looking at the hydrocarbons, and we looked at the hydrocarbons, alkanes ending with A-N-E, alkanes, A-N-E-S, alkane, alkanes, the plural, and we have alkenes, E-N-E or E-N-E-S for the sum of alkanes, and we have alkynes. So alkanes, alkenes, and alkynes, single, double, triple bond. And we talked about this. One of the typical reaction of the double bond and triple bond, they can open up their double bond. If you look at this one here, what's the name of this? Somebody will tell me. It's already there. The name is propene, correct? The name is propene, E-N-E. Why is E-N-E? Is the number of carbons is 3. That's prop. Carbon is 3. Carbon, number of carbon is 3. That will be prop. Okay, guys? And then you'll add to it E and E and E at the end. Oops, sorry. Ne. So now I can add to this double bond. It will open up and I'll make single bond. So out of this, I can add H2O, making an alcohol. And alcohol is preferred to be in this second carbon because it has to do with the mechanism. You don't have to memorize this mechanism. Nobody will ask you, but at least you know the OH at the carbon 2 makes a secondary carbocation, and secondary carbocation is more stable than the primary one. The best one is more stable and is more stable and more realized is the tertiary alcohol. The tertiary alcohol more stable and is solid at room temperature. So this part here will not be. This will make what it's not primary alcohol. Primary alcohol means the carbon is connected to the first, the OH, the alcohol here, hydroxy group is connected to the first carbon, and that's not really true. That's prime will be primary carbocation mechanism, and that's not stable. The secondary one, the second carbon is more stable carbocation, and therefore the OH will be the second. Okay, so now, any question about this? We'll go for the second one, and we'll clear all our nation. We are going to the reaction here. Here, the same thing, the double bond, the same thing we say. The double bond, I'll let in here, somebody here. So the double bond will open up to make single bond. And according to the carbocation, we say tertiary is more stable than secondary, the more stable than the primary. So like tertiary is you have carbon that carries the OH connected to what? To three substituent RRR. So that's a tertiary alcohol. So the carbon this is a cation here is positive, and the OH is negative. So the tertiary is more stable compared with the secondary one. The secondary has only 2. Has only what? 2. H here, and it has 2 substituent R and R. That's the secondary one. OH minus. So this is secondary carbocation positive. Here is positive, and here is negative. And the primary, which is the least stable, which is connected, you have two hydrogens, only one R and two hydrogens. This is positive, and the H minus is negative. In this case, you have the chlorine is negative, and the positive is H plus. We are looking at what? We are looking at this more stable situation, which is, we say, the tertiary one, this is the most stable one, followed by the primary one. It has two substituent, two R's. Here we have three R's in the tertiary. Secondary, we have two R's, and one R is in the primary. Primary means one R, one substance. Secondary, you have two substituent, and tertiary, you have three substituents. So, and we are expecting this one here will have the chlorine will come attach itself to the second one. Why? It will make this one here, will make tertiary, not tertiary, will make secondary carbocation, which is carbocation, which is much more stable. The same thing with the second example here. If you look, if you wish, the second example here, the OH will connect itself. Can you see it to the second one? Not the first one. The first one is not observed. Not the first carbon. It's not observed. That will be to what? To primary carbocation, which is the least stable. So that's secondary carbocation. This is secondary carbocation. You know, it's positive. This carbon, the second one is positive, and the chlorine is negative. And this one, the OH is negative, and the chlorine here is positive. Okay, guys. So this is the big advantage of the of double bond and triple bond. They open themselves up, and you can add to them. Now, this is possible in alkenes and alkynes. However, this one here is not possible in alkanes. Why it's not possible? Because all the carbon atoms are what? Saturated, full. They can't add. They can't eat too much. So they are really full. Now the double bond, triple bond means those two types of bonding. The carbon is not full; it's hungry. So the double bond and the triple bond can open up, and the carbon can take in extra molecules to it, can eat some other molecules into its stomach. Literal. So we can add to double bond, triple bond, but we cannot add to single bond. That's the whole idea. We can add to double bond and triple bond, but we cannot add any molecule to here. So let's look at the next one. Here's the same thing, guys. You have a double bond. Again, this is a double bond here. This is a double bond. Okay, it has a methyl group and one double bond, and we have this negative and this is positive. Well, it turns out to be the eye will not be connected to the other side. So you have this one is not observed. Why it's not observed? Because if it's connected to the first one, this will be 1 and 2, correct? That will be the two R's. That will be primary. But if it's connected to here, it will be tertiary. So the carbon here is connected to three R's. One, this is one R, correct? The rest of the molecule here, from here to here, another R. and the rest of the molecule from here to here, another R. So this is tertiary carbocation. It's more stable. But this one here will be what? Secondary. Because then you have this iodine will be, this carbon here will be connected to the rest of this molecule here and to the rest of the molecule here. That's two, that's secondary. So that's not observed. Secondary, the tertiary is more stable than the secondary one. So again, I don't want you to memorize the mechanism, but at least you know why it's preferred this position. This position is preferred because of the fact that tertiary carbocation is more stable than secondary, more stable than primary. Tertiary carbocation, they have 3 carbons, 3 substituents connected to the carbon, and the 2 substituents connected to the carbon, and the primary, 1 substituent connected to the carbon. So tertiary is more, by all means, more stable. Here, an example here, I added protons, and as you can see, where it will add itself, you can tell me. So you can really predict where it will add itself. So it looks like we have 1, 2, 3. So the most stable ones, so it will add itself. If it's add itself, it will add itself here. Double bond will open up, correct? So then the hydrogen will come out. Then you will have something looking like this, isopropyl cation. So this is what? This is primary. This is R here, guys. This is R. This is another R. So the carbon that carries 2 R's, that will be secondary. But it will be never here. That will be what? The rest is R, only 1 R. That's a primary, which is least stable, not stable. Okay, guys, this one is not observed. It's not stable. That's a primary carbocation. And here you can see the positive here. This is secondary carbocation, 2 R's. So that's the stability it's coming from. Yes. Ask me if you have any question. This is just what we have talked about in a couple of minutes ago about the tertiary here. How many R's we said? 3 R's, 1, 2, 3. Tertiary carbocation is more stable. Secondary has 2 substituent, 2 R's. Okay, the second, and this is primary, is the weakest one, carbocation, and this is very rare found. This is just a methyl that's very unique. It's not really observed, but we are always dealing with one substituent, 2 substituents, or 3 substituents, 3 R's or 2 R's and 1 R. Don't worry about this. This is not observed. Very unique type of methyl cation. But anyway, so then you have primary more stable than secondary, more stable than primary. And this will give us the reason behind Markovnikov products. Markovnikov products is when you add molecules to the double bond. The addition will be affected by the stability of the carbocation. So this is the stability. This is number 1 stable. This is number 2. This is number 3. This is not observed. Don't worry about it. Okay, so therefore you will see the Markovnikov is a Russian scientist, and he dealt with the double bond addition We add the double bond, open up the double bond and add it to the molecules. So the addition only shows that the tertiary more stable in the addition when the double bond opens up than the primary, then the secondary, then the primary. The primary is the least stable. So um, okay, now,
I have a question.
yes.
On the exams, are we gonna have to find the products of those are we gonna have to find the products of those reactions?
Well, yes, and the good thing is you'll get all the multiple choices. So it will be not difficult. By elimination, you can, with the simple knowledge of the rules, that tertiary is more stable than secondary, than primary, than the primary. Then you can tell that by elimination of those multiple choices, you can tell that's what you can expect. And all those exams and quizzes are open book. Though not the final exam. The final exam is not mine. The final exam belongs to the department. And the whole campuses, including downtown, I mean, will have the same exam, final exam. But all my exams inside the class are open book in iCollege, and the quizzes. So now if you don't memorize this and this open book, you can go by elimination. Tertiary more stable than secondary, more stable than the primary. Okay, that's answers your question.
Yes, a little. Question
Yeah,
also.
but the final exam you have to memorize at least the rules of Markovnikov, for example. The addition of a molecule to the double bond, that's Markovnikov, will be affected by stability of the carbocation. Tertiary carbocation is more stable than secondary, more stable than the primary. That's what it says. That's the rule, correct? Let's look at some examples. Let's look at some examples. Um, we looked here. This is Markovnikov, correct? So now Markovnikov will tell you that it will add itself to the to the substance or to the tertiary or secondary. Primary will not be observed because that's not stable. So now Markovnikov will tell you that opening up the double bond should yield the molecule according to the rule. Tertiary carbocation is more stable than secondary than primary. Now, if you look at this one here, this carbon here is what? Primary, tertiary, or secondary? What do you think? This carbon.
Secondary?
This is secondary. Perfect. Why? Because you have two R's. This here you can consider it R, and this one here is R. So this molecule will be observed. But this is primary because all the rest is one R here. Correct? I mean, the rest is here, sorry. The rest from here. So this
Wouldn't it be
carbocation,
tertiary though?
this one here? No, not
Yeah.
tertiary. That's a primary. Here, C, H, H, and the carbocation is the first one. And this is R. This is H. So that's not tertiary. Tertiary, you have, instead of this H, you will have to have R. Instead of this H, you have to have an R. Group, methyl group, ethyl group, whatever. This is R here in this case. What? This is a methyl group, not a methyl, ethyl group, two carbons. So this is ethyl group. So that's ethyl group, 2 carbons connected to this carbocation.
Okay.
So that's not stable. That's not stable. That's primary, connected
Well,
to one group. This one connected to 2 groups. So that's secondary, which is more stable than the primary. Make sense?
yes, it makes sense. But if it was on the other side, if we say for the metal, for example, would it be primary as well? Like the one on the other end?
If we have something like this is our this make because tertiary you have to have at least 4 carbons. You cannot have 3 with tertiary. You have
Oh,
you have to have 4 carbons. Correct? You have to have 4 carbons. Here, look, R. That's 1 carbon. R, 1 carbon. R, 1 carbon. That's the 4th the carbocation with the charge is the 4th one. Correct?
okay.
So you have to have 4. Okay? So Markovnikov will tell you that stability of the carbocation means positive carbon, the charged cation is depending on the how many groups are connected to this carbocation atom. The tertiary, the 3 R's, the 3 substituents are more stable than the two like here. This we have 2 here. Then the just 1 R. 1 R is primary, which is not stable, not observed, but this one is observed. But if we have 4, then this one will be not observed either. We have 4 here, 4 carbon. Then only we'll see the observed is the tertiary, 3 carbons, and the 4th is the carbocation. Make sense? So let's look at the now with this type of behavior here, this is a reducing agent. So first you are reducing the molecule. So we are reducing the molecule, the whole thing here. And then that's a reduction. You're reducing means you're lowering the charge. And then you come back and then oxidizing, that's hydrogen peroxide or dihydrogen dioxide. That's an oxidizing agent. This is a reducing agent. Correct? That's a reduction. And this is oxidation. So first you reduced, okay? And then you oxidize and you add in a basic solution. So you make a complex boron here, hydrogen. Instead of the hydrogen, you can make 3 of these groups. R, 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 correct? Instead of the hydrogen. And the hydrogen will add up to whatever there. So then you oxidize the whole thing. You can make out of this an alcohol. So let me show you here. Make out this an alcohol. So let me. Okay, that's the reaction here, guys. So this is double bond here. When you add to this one here, reducing agent first, it will be reduced, and then you oxidize whatever is reduced with the presence of basic solution. You get an alcohol. Now, according to Markovnikov, that's not possible. To the rule of Markovnikov said, you cannot have this is primary. According to Markovnikov, you have to have secondary. That will be your R. This is your R. So your addition will be here, according to Markovnikov, which is here. Look, see here. Here we don't have a reducing agent or oxidizing agent. We have just a catalyst. This acidic medium. Correct? This is acidic medium. We added H2O. makes secondary. This is R, this is R, and the OH will be the second, will make secondary. This is secondary carbocation. Here, however, the carbocation is primary, and you said primary is most impossible. This rule here called anti-Markovnikov. What? Counter Markovnikov rule, or anti-Markovnikov rule. Why? Because you should not have the Markovnikov tell you tertiary is accepted, is more stable than secondary, than primary cannot be observed. But here tell you no, the primary observed, not the secondary or tertiary, and was proven by experiment. Why is that? Because you are going through what? Through a condition of reduction with this boron trihydride. It's a very strong reducing agent, and then it's a strong oxidizing agent, hydrogen peroxide. First you reduce, and then you oxidize, then you get the alcohol as a primary, which is according to Markovnikov. If you don't add those items, reducing and the oxidizing agent, you will get the OH, the secondary position. So that's what it says. So we have Markovnikov, according to the stability of the carbocation, tertiary more stable than secondary than primary. But we can flip this one here. We are using reducing agent first, reduce the whole double bond, and then we add oxidizing this whatever left over to in the presence of basic solution. Then we can get a primary alcohol rather than secondary. That's counter or anti-Markovnikov rule, counter Markovnikov rule. So let me show you here. Can you see what's happened here? So now when you first you reduce, you open up the double bond, correct? The double bond is opened up. And instead of the hydrogen, now the hydrogen is adding itself up. See here? If this the whole thing is, the double bond, everything is opened up, and you have 3 of them here, correct? And boron. Now you oxidize this in presence of sodium hydroxide. You get what? You get the primary alcohol, not secondary. So the OH is not here. The OH is not here. That's not the case. If the OH is here, that will be Markovnikov rule. But this one, because you are using two agents, one reducing agent and one is oxidizing agent in the basic solution. Markovnikov always in acidic medium. And this one here, anti-Markovnikov or counter Markovnikov addition to the double bond, is in a basic solution. And you'll be using a reducing agent and oxidizing agent, both. Correct, guys? So you might put this one here in a note. So whenever there's a question, so you can answer it. It's, as I said, repeating myself again, it's an open book, but the catch on this, everything is timed. So you'll have time is accounted for. I think I'll put it 90 minutes or so. So then you have to always look at the time so you don't surpass the time, and then you cannot answer your question correctly. So, okay, guys, so let's see here. What alkanes is needed to obtain the alcohol here below? What alkanes is needed here, guys? Somebody will tell me. We need alkenes here. What alkenes is needed? Somebody will tell me. Come on, guys, you can answer this question. So
it has double bonds.
Yeah, so here it is. I put this one here so you can visualize the whole thing. This is, yeah, So I put this one here and put the carbon here. Hydrogen is here. Hydrogen is here. Correct? Hydrogen is here. This is a primary one, correct? Hydrogen is here. And the OH is here. So I need, so maybe I'll make it easier for you so you can follow me much better. So let me take the OH from here. Okay. Then say the OH is here. And the H is here. So I need a double bond. So where can the double bond come? Well, it turns out to be, if I change the color here, so it turns out to be, I can what? Eliminate this one here as what? H2O, correct? Move them out. So I'm moving this one here. H2O out. 2 hydrogen, one oxygen plus. Now we are talking. Now we are talking with them. C H, correct? Now the H is down here. H is here, down, and in the top, see here. So it is double bond, C, correct? H down and H side. So the double bond will come in between those two. Double bond will come in between those two. And one of the hydrogen, correct? One of the hydrogen will be out, kicked out as H2O, correct? So one of the hydrogen will be kicked out as H2O. Make sense, guys? Make sense? So you pull out the hydrogen here out. This is out. And the remaining for you this. That will be here, double bond then. Double bond will appear here then. So that will be it, correct? That will be, let's take the H2O out and then you have this alkene. When you add H2O to it, then you'll have this OH will come here as a primary one, correct? So as a primary one. So let me.
Excuse me, I don't
Yes.
get it. So for this question, do you just have to rewrite it or just give the product?
No, you have to tell what alkenes you need to obtain this. So this one here. So then the alkenes you need is this alkene here. Yeah, this alkene you need. Plus H2O. Those two here, ingredient here, will give you what? Will give you this. So the H2O will add itself. Are you following me here?
Yes, I am.
Now, tell me if it's Markovnikov or counter Markovnikov. Come on, you can't tell me that. Can we apply Markovnikov or counter Markovnikov? According to
I don't
this,
get the question. I'm not sure.
well, listen, the OH is now connected to the first one, correct?
Yeah.
To this one. This is second, this is third. So this is what? Primary, secondary alcohol. This is primary.
Okay.
That's a primary. And that's a violation of Markovnikov. Markovnikov will tell you the more primary is not stable. You should not get any molecule out of it. So this molecule here came through what? The reducing agent this one here first, and then the oxidizing agent in presence of hydrogen peroxide, in presence of the basic solution or basic medium. You understand my point? So this is counterclock or anti-Markovnikov rule, because Markovnikov will never support primary, because primary is the least stable ever carbocation, the least. So it has to be tertiary or secondary to get the molecule stable according to Markovnikov. But here is connected with the first one. That's a primary. So the primary is only through this oxidation reduction processes in a basic solution. Make sense? So this is counter Markovnikov rule, not Markovnikov. Markovnikov will go by the carbocation stability. By what? By the carbocation stability. So let's take see here. Here is the same thing. Here we have what we call this type of reaction. It's not written, but we know that we have a double bond, correct? Here we have a double bond. As you can see, we have a double bond here. Correct? That's a double bond. This is R. And this is R. And those are sticking towards me, not in the back of the molecule, towards me. What is this, cis or trans?
Cis.
That's a cis, correct? Because both R group, methyl group is sticking at the same direction, the same orientation in space, correct? Not if one of the arrow here, suppose this arrow is made like this, you know, like striking lines, that means this methyl group in the back, so that will be trans. But since the bold arrows means they are sticking at the same orientation in space, and they are in the cis position, the cis position. So if I have, you know, this like line here instead of the solid arrow line, arrow made of lines, that means this methyl group is sticking in the other side of the molecule, which will be trans. Anyway, now this double bond here can be what? Can add to it hydrogen in presence of platinum as a catalyst. What we call this type of reaction, somebody will tell me?
Hydrogenation? Something like that.
Hydrogenation, perfect, correct. So that's the catalyst here. The catalyst is carrying out the hydrogen at its surface. That's the surface of the catalyst. Now the surface is of the catalyst holding what? The two hydrogen atoms. And then they will allow the reaction without catalyst cannot proceed. So therefore, this type of reaction called, because you are adding hydrogen, this is hydrogen, the same word, you are adding hydrogen, and then you add just NaTiON, hydrogenation. Make sense? That's another typical reaction of a double bond. Hydrogenation, it's adding, it's the open up of the double bond or the triple bond as well. So you can add hydrogen to them. If I add OH, H2H, what type of reaction is this? If I
Hydration?
Hydration, correct. So hydrogen, pure hydrogen is hydrogenation. Here just called hydration. Hydration means hydrate means H2O. Hydration. Okay, those are type of the reaction of the double and triple bond as such, both of them. They can react similar. So this one out. This is just to show you the carbocation, guys. This is the carbocation stuff. You don't have to worry about the mechanism. Nobody will ask you. This is higher chemistry, but always remember, this is what, tertiary or secondary or primary? Which one? What type of carbocation is this? Come on, guys, don't let me down.
It will be tertiary?
Tertiary? No.
No.
This is the whole thing is R, correct? You can add the rest of the molecules R. This is another R. So this is what?
Secondary?
This is secondary, yes.
Oh.
Secondary is stable than primary. Tertiary is more stable. You have 3 R's. If I replace this hydrogen with another dangling R here, that will be tertiary, but I don't have a third one. I do have only hydrogen here, so 2 R's and hydrogen, that's secondary. So you can see the secondary, you can add to it, and then you can reduce what? And this one is what? What we call this one here? That's it can show you how.
Primary.
This is primary, and according to Markovnikov, this will win. Okay, but here they show you that you can flip back and forth with them, but according to Markovnikov, the secondary carbocation is more stable than the primary one. Correct? Just to show you the carbocation mechanism. You don't worry about this. Nobody will ask you unless you are going for higher chemistry. Then yes. This is another type of reaction of the double bond and the triple bond. This is called polymerization. Polymerization, you add a molecule, you make a polymer. So like polyethylene, that's from ethylene, you add to it every time a unit of ethylene. Ethylene means has 2 carbons every time, 2 carbons every time. And you make a plastic bag. That's you put your fruit inside, your meat inside, and put it in the fridge. So that's a polymerization. Polymerization is adding molecules to the original molecules and make it bigger and bigger and bigger in molar mass. And therefore you make a polymer out of it. And most of the time those polymer are plastics bags, plastic piping for plumbing. All those stuff are polymers. All those stuff called polymers. So plastic bags, plastic tubes used for plumbing. So, and that's just to give you an example here. This is 2 carbon, 1 double bond. That's an 2 carbon is eth, and then ethene, correct? That's 18, the commercial name called ethylene, but we go by the IUPAC name. We just forget about the common name or commercial name. We say this is 18 with double bond. Then what we are doing with this, we are adding this one unit-wise with the help of what? Of a catalyst. You need a catalyst. So we're adding to this compound here units of what? Of this 18 double bond. So every time we'll add, so you can add them here. We have 1, 2 carbon, correct? Now we have this one, our 1 and 2. We added what? We added new. Those are new we added. Then you can keep adding those. This is 1 and 2 started with. You can add this one here. And you can add this one 2 units, another 2 units, another 2 units. So you can make out of this real bag. Let me show you here the picture of this. Let me show you the picture of this in a minute. So hold on. It is. Let's look at this picture. That's a small tiny child. He is holding to the what? To the plastic bag, with the plastic bag, because now you have added every time 2 units of carbon, 2 units. That's ethene or ethylene, called ethylene. So that is The commercial name is polyethylene, but that's polyethylene. You know, that's polyethylene. So we added 2 carbon units, 2 carbon units, double bond. So then we have huge molecule, which is this baggie. The small tiny child is holding this plastic bag. You keep your fruits inside. I think he has an apple somehow. Or yeah, no, he has fish. He has 2 fish inside. I think golden fish. So you can hold fish inside. You can hold meat. You can hold fruits inside. That's a polyethylene. Polyethylene. This is a commercial name. That's really, we added 2 carbons. Those ethene, polyethylene, but the commercial name is polyethylene. So, and oxidation with permanganate, that's a chemical test inside the lab. We talked about this, if you recall, that's in the lecture last week. The single bond, if you put bromine inside, the addition will not occur, single bond. If you add bromine to the double bond or triple bond, they will open up. The bromine color will disappear, will be colorless. Now the permanganate is a very strong oxidizing agent. You can oxidize this double bond. So the permanganate will be reduced to manganese 4 oxide. That's a reduction. This is a reduction here. This is a reduction, correct? And the double bond here will be oxidation, will be oxidized to dialcohol. This name of dialcohol called glycol. Somebody will tell me where we use glycol for? In our cars? Somebody will answer the question. Come on, guys, you can answer me. That's antifreeze. This is the antifreeze. That's glycol. So we use this compound here. We use this compound for antifreeze, so to keep the temperature cool and not overheated. So the permanganate is turning from purple, that's a purple color, to the brownish black color. That's, you know, there is a reaction because you see the change of color here from purple liquid to a solid. This is a solid here. This is a solid. This is a liquid solution. So from, you can see this is permanganate here, purple, then it turns out black, brownish black color. So there is a reaction, and this is called oxidation with a very strong oxidizing agent called potassium permanganate. So okay, guys, this reaction, the same thing here. You have a double bond oxidation reaction. This is another example here, guys. This is oxidation in presence of a catalyst in acidic medium. You can make out of butene formaldehyde. Formaldehyde is used as a preserver inside your biology lab, preserving dead bodies. And this is what you get out of the oxidation of the double bond. Double bond can be oxidized further to formaldehyde, and can be further, you get out of it, you can further oxidize this one here to formic acid, formaldehyde to formic acid further. And you get beside this the aldehyde, another aldehyde. So you have 2 aldehydes. You have 1, 2, 3, 4, 1 and 3. So you have 2 aldehydes, 1 propanol, one is formaldehyde or methanol. This is methanol. This called the IUPAC name is methanol. This is propanol. Okay, guys, and we can oxidize further those here, and you can get what ethanol. That's what I said. This is This is three carbon propanol, 2 carbons. If you have 2 carbons here, you get what? 2 ethanol. Depending on what the condition you are using, you can get this, or you can get this one here, depending what condition you are using. So guys, this is just type of reaction. Again, you don't have to memorize all this type of reaction, but at least you will know you will know what you can expect after oxidation. Oxidation are always will give you an alcohol of the double bond or aldehyde, whether it's alcohol or aldehyde. This is the double bond. Now about the triple bond. The triple bond is, we talked this one in the class already. We said the single bond, it has a hybrid called sp3 hybrid. So each carbon will come up with the hybrid sp3, and if you look at this is the geometry is tetrahedral. Tetrahedral, correct? We talked about this last week, and the angle is 109.5 degrees, correct? And the double bond, we said the hybrid of each carbon coming together to make a bond here. So this bond is sp3, single bond. This is single bond. The double bond sp2, each carbon will come with the hybrid is sp2 to make the combination between them. And the geometry is trigonal planar. Trigonal planar, correct? And the angle is 120 degrees. The last one is the triple bond, which is here. The triple bond is bond. Each one will come with sp. Each carbon will come with sp or hybrid, and the geometry is linear, and the angle of the linear stuff is 180 degrees. So you should really memorize this. Is very important because it might come anytime, so you can see what type of bonding you have. The triple bond, they have one single bond and 2 double bonds. The double bond, one single bond, 1 double bond, and the single bond does not have any double bond or triple bonds, correct? So that's about the sigma, and all this one sigma, that's a triple bond. It has 2 double bonds here, as I said. It has two double bond and 1 sigma bond, 1 single bond. Sigma means single, and the bi bond means double. So, okay, guys. So we're almost there with the chapter. So let's look at the this is how you can make from triple bond single bond, but all the time you have to go through what the triple bond will open up. Yes, but it has to open up through what? Through the double bond. We have 3 triple bond, 2 double bond, and 1 single bond. Three bonds here. So you have to go first to get out of this double bond, triple bond, double bond. And then from the double bond, you get what? Single bond. This is addition of the bromine. So first you open up the triple bond to make a double bond. It adds itself into this one here. This is the trans, opposite to each other. And then you add up to this, and then you can see of all those addition there. This is now alkane. So we started with alkynes here to alkenes. And from alkenes, we went all the way to alkanes. So that's always the case. Triple bond goes to single, double bond to single bond. Just show you the same thing, addition here. The double bond, you can add to the double bond. This is sodium, this is a salt. This is sodium imide, NH2 minus, that's an imide, sodium imide. And the basic solution, liquid ammonia is a basic solution. So what will happen is you pull out one of the, one of the hydrogen will be pulled out. One of the hydrogen here will be pulled out. Not the R cannot be pulled out. This is a big junky substituent, but this is very loose, can be taken out. And you put the sodium, this is negative here, because you put one hydrogen, you put H plus. This will go back out in the solution as H plus. So the carbon will be minus. Then the sodium will come out to make a solid, a solid salt. Sodium will be sodium, the acetylide, and ammonia. So this is a salt here for the triple bond. Now the triple bond, you can add OH, like a Markovnikov, in acidic medium. So you open always, you cannot open all of them at once. Always triple bond, you open it to double bond. And then from double bond, you can open it to what? To single bond. So here, you cannot jump from here to here. That's by all means, no, it's not allowed. So you have to open up the triple bond to the double bond first, all the time, and then to the single bond. This is what we talked about, guys. Correct. This one here, sp3 tetrahedral, correct. That's single bond, correct. Tetrahedral. This is, I will say, add to this one here, guys. This is alkanes. Alkanes. ANES. This one here, sp2, will be what? Alkenes. Double bond. And this one here is Sp, that will be your alkynes. ALK, Y, NES. So that's, we talked about this hybridization. This one is sp3. This one sp2, double bond. And this one is P. Correct. So let's go further. This one, another example here. You can, the hydrogenation of the double bond, we talked about it. You need the platinum, is the best. You can add palladium to it, or you can use palladium by itself, or nickel. All those are catalysts, can be used for this hydrogenation. So you can add any halogens to the double bond. And as you can see, always you have these two types of addition. You have 1,4 and 1,2. So 1,4. So memorize this addition of the double bond, preferring 1,2. If you have four carbons or more, 3 carbons will not work. You have to have 4 and more to see the 1,2. addition of halogens like chlorine here, for example, or bromine, or 1,4. Those are the preferred two type of addition. So the last thing here, this is another addition here, double bond. Again, you have what we said before, you have 1,2 addition, but you have to have 4 carbons and more. 3 will not work. 3 carbons, the addition 1,2 or 1,4 will not work. You have 1,4 addition, carbon 1, carbon 4 here. Here carbon 1 and here carbon 2. So you have 1,2 addition or 1,4 addition. Okay, guys. Here the same thing, you can add to this two double bonds, another 18 here, and the 18 will come and you can get a cyclic, you can get a cyclic ring. So you added this one here, you opened up the double bond of this 18 here, will add itself up. Now the double bond was moved out, correct, and you have one single bond. So what's the name of this compound? Somebody will tell me. What's the name of this compound? Somebody will tell me, the last slide. What's the name of this compound?
Hexene? No?
No. You forget your name. Your name is correct, but
cyclohexene.
Yes, cyclo. It's a cyclic, correct? Cyclo,
Yes.
and then the 6 carbon, hex. That's 6. So first the ring. I know why it's disappearing. So this is cyclo, then cyclo means start with the ring, and then hex, 6 carbon, hex means 6, and then you have ene, that's a double bond. Now, we have only one ene, we cannot say this is always 1, so we don't have to write 1 ene. But if we have more than 1 double bond, then we have to number them where they are located, correct? If I have here another double bond, what's the name will be? That will be my 1, 2, 3, correct? Will be X, 1, 3, this is 3 here, 1, 3, 1, 3, what will be? Diene, correct, guys? So I have 2 double bonds here. This is my 1, this is 2, this is 3. So it will be cyclo, X, 6 carbon, and then 1, 3, those double bonds, 1, 3, diene. So I have two double bonds. And the last thing here is out. This is the last slide, which is, we talked about this catalyst. This is ethene, make out of it a polymer. This is the mono units, or the most important unit in the polymer. You add itself to the n number, how many units, 100 units, 200 units, you make out of this plastic. So that's so this is they call it monomer. Monomer means a unit that repeats itself 100 times, monomer. And the end product, how many monomers you have, how many n number, 100, 200, 300, you make what? Polymer. So they end up with having the same MER at the end. So here it is, mer and mer. Make sense? Mono means one single unit that repeats itself. When it repeats itself to the final units of 100, 200, then it stops there. Then you call it polymer. But if it's single unit, you call it mono. Mono is one, monomer. Then if it's coming and stops at whatever the number is, N is, those 300 units, 500 units, then it will be polymer. So, and here you can oxidize the double bond we did, and you make those two hydroxy alcohol, or they call it glycol, and that's our antifreeze. That's the antifreeze. If you have R as H, R is replaced by the H, that's called glycol. So replace R with the H, that will be your glycol, and glycol is used as antifreeze. So we have still 7 minutes. You think we can go for the next chapter? I think a little bit. Everybody's listening? Or just tired from listening? Hello?
I'm listening.
We're listening.
Okay, then let's look at what the next chapter we are expecting. At least get the glance of it when we meet this coming Thursday. We'll finish it. So, but at least we get some feeling about it. Correct. So this chapter is really done. And stop sharing and open the PowerPoint for the stop sharing. And I will open up the next one. The next one is chapter 12. And by the way, those PowerPoints, you got them correct. They are in 10, 11, and 12. So let me just put this one quick. We have 5 minutes. Please get the idea what we are dealing with. So maximize this. Let's share. Let's share PowerPoints. Share. Okay, so this is chapter, we did 10, 11, and 12. We finished 12, and we put quiz number 1, exam number 1. So this chapter about alcohols, correct? And what really we are interested in, if you look at this, we are interested in looking at alcohol. Alcohol in general is R, then OH. So this is the general molecular formula or structure of the alcohol. So let's get the red one. The thiols are R, SH. Are the thiols here. The phenols are alcohol, but aromatic alcohol. So the phenols looking like this. It is the benzene ring. And this is a benzene ring, and then you have OH. That's a phenol. Now, in isophenols, then you can have any substituents hanging around this, but the main structure here is this here is here without the R. This is our phenols. The ethers, on the other hand, the ethers will be looking, let me see here, change the color maybe. The ethers here will be looking, so you look at the ethers looking like this, R, and then in the middle oxygen is R1, and this is R2 here. Two groups of R, and then in the middle is oxygen. So in the middle is oxygen. That's called ether. So we have 4 different functional groups, and those will have different type of physical and chemical properties. What is really in common, in the common of the all of them is the presence of oxygen like in alcohols and phenols and ethers, the presence of oxygen there. See here, it's very important to have oxygen there. And the presence in thiol is very unique. You have a sulfur. So the presence of oxygen, hydrogen, and in the sense of thiols, you have what? You have sulfur. Now, the good things about them are polarity, so they can differ physical properties I'm looking at. The alcohols in general, the smaller amount, the smaller molar mass of alcohols and thiols, the smaller amount, the molecular mass is not that big. Those are polar. Ethers in general, they are not polar. Phenols are polar, polar, polar. Ethers in general, they are not polar. So the restriction of the electronegativity atom of oxygen is restricted with the size of those big R's there, making the ethers are not polar. But phenols is polar, and they are acidic because they can donate their H plus, this phenol can, and they get phenolate and anion here, O minus and H plus. The H plus can be donated as an acid. So phenols are weak acids. Alcohol is not an acid or base. Thiols, the same thing. They can give away their protons. But ethers, they are not polar. They can't be acid or base or anything else. So alcohol, the same thing. They cannot be acid or base. The phenols, they are acidic in character. Thiols, acidic in character. I'll stop here, I think, and we'll meet Thursday to finish up chapter 12. Chapter 12, lucky we are not spend that much time on it. Very, very short. The second chapter is so comprehensive that will set up the rules and everything, naming for the rest of the whole chapter. So chapter 2 is really putting the foundation for all the other rest of the chapters. Any questions so far, guys? You'll get the recording tonight if we are lucky. If not, by tomorrow. So it has to go through WebEx portal, and they have to check its content because it has to go to a GSU portal. They check the whole thing because it's not anything is illegal or something, they will discard it. But we have only legal stuff here. But anyway, so it takes hours to bring it back to the instructors. So it takes a couple hours. Maybe I'll not be able tonight. Maybe tomorrow morning I'll get it. Anyway, so any question you have? This is chapter 12, the third chapter. And then you will see from now on the chapters is very, very short. Physical properties, chemical properties, that's it. And that's it. And chemical reactions. So not like the chapter 2 that's had put the basic foundation of everything. So any question you have? Any question? I'll stop sharing now. I say any question you have?
No.
Then I'll say good night. So I'm tired. So I'm today the whole day in the hospital. So okay, guys, I will see you Thursday.
Okay, take care.
Good evening. Good evening for all. Okay. Bye. I will stop the recording.